I thought we'd take a look at what are the more interesting things you can get on eBay and you can build up for your lab. It's a Rubidium frequency standard, in this case the FE-5680A. You can get them pretty cheap on eBay, so I thought we'd do a teardown, I'd build one up, see how it works, and maybe build it into a little custom case and hook it up and use it as a lab frequency standard, primarily for my frequency counter, but you can use it for anything. Let's go. So what exactly is a Rubidium frequency standard? Well, inside this little can, which you can get for about 50 or 60 bucks on eBay, used, of course, you can't buy them brand new for that, not a chance. They're usually, thousands of dollars. But because these are used in cellular telephone towers and things like that to maintain an accurate frequency reference, when they discontinue or they decommission those frequency towers, tons of these things are left over and you can get them really cheap. And what's inside this can? Well, it's basically an atomic frequency standard, and you've heard of that before. You've heard they're used in GPS satellites and all sorts of advanced communication systems. Well, there are a few ways to actually get an atomic frequency standard. You can use hydrogen, cesium, and the other one is rubidium, and that's a very popular one. Bit of a poor man's frequency standard. This isn't going to match a GPS satellite, not by a long shot, but it's pretty darn good, and it's going to be a super accurate frequency reference for your lab. So let's take a look at what's inside it. It's a bit complicated, but stick with me. And here it is. I know it looks complicated, but it's not that bad, and this may not be 100% accurate, so don't bitch about the details, okay? If you want to find the real details, go look them up, but I'll give you a basic rundown of how a rubidium frequency standard works. Shortened to RB, that's the chemical symbol for rubidium. Now what we have here is what's called a physics package. I love the term physics package because it has a bunch of physics inside a little metal can that basically does some magic here with some electronics, with a frequency locked loop, an FLL. You might have heard a PLL, phase lock loop. This is a frequency locked loop where it basically has an internal oscillator, just a regular crystal oscillator inside your standard. It can either be a oven controlled one, it might be that, or it might be a voltage controlled crystal oscillator, a voltage controlled oven one, or digitally controlled, or whatever. There's several ways to do it, but let's just assume it's a voltage controlled crystal oscillator working at a fundamental frequency, which is a multiple of the rubidium transition frequency of roughly 6.834 gigahertz. That's the transition frequency of the atoms. And if you want to find out the exact details of the hyperfine transition of rubidium, the rubidium atom and all that sort of stuff, you can go look it up. I won't go into it, doesn't really matter. But basically, the physics package up here helps, it works as a servo, and it servos this amplifier and keeps it locked to the transition of the rubidium atom inside this frequency package. And then from that, it can just generate your frequency standard out. In this case, 10 megahertz is a pretty industry standard reference frequency. In any good lab, if they have a frequency standard, will have 10 megahertz output, and that's what a lot of, that's what most frequency counters will have an external frequency input for the reference oscillator, and it's almost always 10 megahertz. So that's what we're going to get out of our little rubidium frequency standard today. These are what it puts out, 10 megahertz, but it's disciplined around a much higher an intermittent frequency of 50 odd. In this case, it's 50.255 megahertz, but other implementations of rubidium frequency standards can use different frequencies and different techniques. As I said, ADCs and DACs and digital control. But basically what it does is it has a discharge lamp up here, which actually this takes quite a bit of power, which these rubidium frequency standards do actually require quite a bit of power to actually operate, in the order of 10 plus watts or something like that. So it has a rubidium 87 discharge lamp, If you want to know what 87 is, go look up your physics textbooks. And it has a resonance cell, which is a little cavity, just a little cavity which the rubidium gas atoms will be inside there, and they get all excited when you apply a certain frequency to them. And this resonance cell can get upset by external magnetic influence as well. So it's usually in a mu metal shielded can so that external magnetic fields don't affect it. And there's some other things that they can do to try and reduce the effects of external magnetic fields as well. And then there's a photocell on the output with a transimpedance amplifier to detect the amount of light coming from the discharge lamp. And the whole idea is that when the resonance cell is exactly at 6.834 and there's digits beyond that, which is the hyperfine transition frequency of the rubidium atom, they all resonate, all the atoms inside there resonate, and there's less light going through, or it blocks the light going through to the photocell, and that generates an error voltage out of the amplifier, and then it can servo that and keep it locked in. And they might sweep it by a couple of hundred hertz or thereabouts around the transition frequency from this RF generator here, but that's basically what it does. It just blocks out when it hits that resonant point. The less light gets through the photocell, and boom, and then it can adjust the frequency, and it settles down and locks in. So that's why these things might take a few minutes, or some might even take tens of minutes to actually lock in and stabilize, but once they do, they're incredibly accurate. So it's a basic rundown of a physics package and how a rubidium frequency standard works. Pretty neat. I love it. Magic. So why does all this frequency stability matter? Well, I'm glad you asked. Let's take a look at it in terms of, say, a basic frequency counter. And let's take a look at some crystal oscillators. Now, I've got 4 different types here. One is your standard quartz crystal, which you're probably familiar with, one of these little crystal oscillator cans, or just one of these little, regular quartz crystal oscillators you've used in your projects before. And they're pretty darn ordinary. They're in the order of 10 to 100 parts per million tolerance over a standard temperature range. Basically, this tolerance table here takes into account temperature, basically. So what's 1 part per million? Well, 1 part per million is typically specified on the data sheets as 1 times 10 to the power of minus 6. 10 to the power of 6 is a million. There's 1 part in 1 million, and so on. 10 to the power of minus 7, 10 to the power of minus 8. So these standard quartz crystals are pretty crappy. They're 10 to 100 ppm. And the other thing with any oscillator, whether it's quartz or anything else, they're all pretty much all of them are based around quartz, whether or not they're temperature compensated or they're rubidium compensated. As we've seen, they're going to have not only a tolerance over temperature, but they're going to have an aging factor as well as they get older, and that usually is specified per year, but can also be specified, they can give you additional figures per month and per day as well, because you might want just a very short-term stability over 1 day. But let's just take a look at some typical figures for a year. These things, not only are they not that great, just basically at any one point in time, over a year, they're also going to age. 5 to 10 ppm might be a typical figure per year. So they're just going to get worse and worse. Now, if you look at a digitally temperature compensated crystal oscillator, that's where it's a regular crystal oscillator, but they've actually measured it. They've characterized its performance, and they've actually programmed in compensation values over temperature. So hence digitally temperature compensated crystal oscillator. And they're pretty much, they're going to be like an order of magnitude better, 0.5 to 5 ppm, with 1 ppm aging, order of magnitude better stuff. And then you get onto an oven controlled crystal oscillator. That's where they actually keep a regular quartz crystal like this at a very specific temperature. So the ambient temperature, the temperature in your lab, which drifts all the time, doesn't matter. So they can get very stable in terms of 0.1 ppm, 10 to the power of minus 7 over the span of a year. That's the aging sort of thing, and the tolerance is pretty darn good too. And then you take a huge step up to the rubidium type stuff, 10 to the power of -11 we're talking about, with 10 to the power of -9 aging. Absolutely incredible. And of course these crystal oscillators, they come in all different types of manufacturing, what's called cuts. They cut the crystal in a different way, you know, SC cut, AC cut crystals, and that can affect the temperature characteristics and the aging characteristics and the shock characteristics and all sorts of vibration characteristics, everything for these crystals. I won't go into it, but let's take a look at how it relates to a frequency counter. So here's a typically good old school frequency counter. It's a Philips PM6672. You can pick these up on eBay. I'm going to have to do a teardown of this one. And it's got, well, basically, it comes with several different types of oscillator options. When you buy frequency counters like this, whether they're the one-hung low cheapies on eBay or they're the good ones, you know, name brand ones like this, then you're going to get different types. And if you even this a good one like this, if you buy it just with its standard oscillator option, it's just going to have one of these regular, you know, quartz untemperature compensated oscillators in it. It'll be, you know, a good one, a pick of the bunch, but you're still only going to get you know, 5 to 10 ppm. Well, what does that how does that translate to how accurate it is on the display here? Well, let's take a look at it. This is measuring a 10 megahertz frequency. Okay, so it's actually displaying not in megahertz, displaying in kilohertz there, but it's 10.0000000 megahertz. Now, what's 1 ppm? Well, if it was 1 megahertz, then 1 hertz, 1/1,000,000th of that, 1 part per million, it'd be this least significant digit here. But because it's 10 megahertz, it's going to be this digit here. So if you had a 1 ppm accurate crystal in there, for example, then it would only be accurate to that digit there. So the least significant digit there is absolutely useless. Plus you've got aging on top of that, you've got temperature and all sorts of other stuff. So, you know, if you've only got a 1 ppm crystal, that's not that great, but typically you might get a 10 ppm. Oops, you've just jumped up to this digit here, and the last two digits are useless, not to take into account aging, so it's pretty horrible. So generally, for a frequency counter, this is a regular 8-digit one, you might have a 9-digit one, you're going to want a pretty stable oscillator in it. So if you buy one of those, you know, $100 or $80 one-hung low brand frequency counters on eBay, they're just going to have a cheap as shit crystal in it, and the last 2 or 3 digits aren't going to matter a rat's ass. Now here's the oven controlled oscillator inside this frequency counter. It's got this option, it's got the specific PM9690/01 option, and I've had that on, and yeah, trust me, that is actually quite warm. That's why these things can take 10 or 20 watts of power just to keep them at a stabilized temperature inside. And as I said, inside there, they've just got like a regular crystal in there, but yeah, it's going to be a really stable one. They've chosen it for a really good cut, but because it's kept at a constant temperature, then once you let this thing warm up to temperature, you have to do that with these oven controlled ones. They've got to warm up to temperature first, but once they're there, they're incredibly stable. This one, if you look up the spec sheet for it, it's you know, got a tolerance of in the order of you know, 0.1 ppm, or aging of 0.01 ppm. So pretty darn good. You'll notice too that it's got an adjustment trim pot in there, and these things aren't magic, of course. You've actually got to trim them to the correct frequency, but once you do that, they don't drift much. So having that oven controlled oscillator in here with 10 to the power of -8 aging, then we're talking about the 1 digit past the least significant digit here in terms of aging, in terms of accuracy. We're talking about the least significant digit there. So it pretty much matches the capability, that sort of ovenized oscillator matches the capability of a typical 8-digit frequency counter like this. So pretty much you're going to at least want, if you've got a good frequency counter, even, or if you've got a 9-digit one, for example, with an extra decimal place, you may actually, well, you at least want a oven-controlled oscillator with that sort of stability and that sort of aging for this. But we're going to blow it out of the park by using a Rubidium standard, and we can just feed the 10 megahertz reference signal in the back, and Bob's your uncle. And that Rubidium frequency standard will absolutely guarantee that regardless of aging and temperature and all sorts of stuff, what the frequency you get on your frequency counter is going to be exactly correct to, well, it's going to be plus minus one least significant digit. And that can be important for all sorts of niche sort of stuff you work on. Ham radio as well, having an ultra stable frequency source is a big thing in the ham radio circles. And there's some other timing applications, timing counting applications in the lab where you know, a really good laboratory 10 megahertz reference Rubidium standard is worth its weight in gold, and you can buy them for $50. So, you know, it's well worth building one. So let's take a look at this one we've got from Frequency Electronics Inc. eBay is absolutely flooded with these things, so I'm sure you have no problems getting one for, you know, $60 maybe, including postage, or there might be postage on top of that. But these things probably cost thousands of dollars, maybe, well, maybe not $10,000, but, you know, they would have cost several $1,000s brand new. And they're a brilliant Rubidium frequency standard. This is the FE-5680A. There are several versions of it, and they're all used. You won't pick up one brand new, I don't think. They're all pulled out of old, you know, GSM cell phone base stations or something like that. So pretty much they'll all be secondhand, but if you buy from a good eBay seller, they will have actually tested them. Now this one actually comes with the pin out. It's got a standard D9 on here. It came with you know, the D9 connector and a bunch of flying wires there, and pin 1 is the input. It from 15 to 18 volts DC. I don't know whether or not it can go below or above that, but I'm going to stick within that. It's got 2 ground pins. It's got a frequency lock output, so that you can drive a LED indicator direct. If you put in a box, mount a LED onto there, and I believe it's active low, and that will indicate that it's warmed up and it's locked in, and your frequency output is spot on. It also requires a second input of 5 volts on pin 4 there, and then you've got your RF 10 megahertz out, and it is actually RF, it's a sine wave, and it's 1 volt peak to peak into an open load, or 0.5 volts peak to peak into a 50 ohm load. So let's power it up and see how much power it takes. Okay, let's power this thing up and see what we get. It's got a 15 to 18 volt input, which I'm measuring the current here. I'm using 15 volts on the input, and it's got a 5 volt DC input as well, which I'm measuring the current on the fluke here. So we expect there to be a bit of a power spike at power on until it settles down. So it should start up at a higher current and then slowly settle down to a lower current. So I'll switch those supplies on both at the same time and see what happens. There we go. Well, 1.6 odd amps on the 15 volt rail, and basically just 100 odd milliamps, just under 100 milliamps on the DC rail. And haha, we have, ta-da, our output signal already. And there it is. And it is 10 megahertz at 1.3 volts peak to peak, because there's no load on there, no 50 ohm load, because if we actually switch on the 50 ohm impedance load, of course it will drop down. But there you go. But has it locked in yet? I'll have to probe the logic output and see how long it takes to lock in. But the frequency has actually outputted straight away. Okay, let's try that again. In this case, the yellow channel 1 waveform is our oscillator output. Channel 2, 1 volt per division, that's our lock output. So I expect a logic level output. I believe it's active low once it's locked, so we should actually see it jump up. And I'll switch them both on and we'll time that and see how long it takes. Bang, it's actually high. There you go. So it hasn't actually locked in yet. So we're talking 1, 2, 3, 4, 5 volts. And boy, there we go. There's some something happened to the RF output there, but it hasn't locked in yet. We should, after a minute or so, we should see that green line, the channel 2 line there, drop to logic low to indicate that it has locked in. Bang, there it goes. And it's now locked in. And what values have we got down here on the meters? We have about 0.76 amps there, 0.77 amps on the 15 volt rail, and 90 odd milliamps on the 5 volt rail. So as you can see, it actually draws a fair bit of power. So that's almost 12 watts total power consumption for the device. And it only took about 35 odd seconds to lock in, so it wasn't that long at all. And that case is getting pretty darn warm too, and if we try and attempt to probe that, we're talking, you know, it's well over 40 degrees, and I've only had it on for like 5 minutes. So these things can actually get quite darn hot, so you wouldn't want to mount this thing in like a sealed plastic jiffy box or something like that. It just gets stinking hot. What you want to do is mount one of these in a die-cast alloy case or something like that, one of those extruded aluminium cases or something that you can get the heat out of this thing. I don't know what temperature will do to these things long term, and well, I don't really want to know, I think. So yeah, it'd be much, I think it'd be very beneficial if you kept these things as cool as possible. And there you go, we're almost getting 50 degrees. There seems to be a hot spot over this side of the package over here, but it'll, yeah, they get pretty darn warm. Now there are a couple of options on this specific model. One is to actually get an RF output, separate RF output connector here, and also there's an option to get digital frequency control, so that I believe it's like some sort of serial input, RS-232 type input, and you can send commands to it to actually generate a specific frequency from 0 to 10 or 20 megahertz or something like that, and that'd be really nice. But I don't believe this model actually has that. It's just the fixed 10 megahertz output. But if you can get that one with the digital frequency control, that would be really nice. You could turn one of these into a really nice fully programmable lab Rubidium frequency generator with a keypad and a microcontroller and LCD, and you could set the frequency to anything you wanted. It'd be terrific. But we've only got this fixed 10 megahertz one here. Ah well.